You know, we rely on databases for literally everything, from our bank accounts to booking a flight, and we trust them. But have you ever wondered how they actually protect our data? Like, what stops it from just vanishing into thin air during a power outage or a system crash? Well, today, we're going to pull back the curtain and uncover the ingenious, invisible safety net that keeps your entire digital life from falling apart.
So, picture this. It's a heart-stopping scenario, right? You're sending a friend $100. You see the money leave your account, the balance drops, and then poof, your banking app crashes. Your friend checks their account. Nothing. The money isn't in your account. It's not in theirs. It's just gone. That right there, that's the fundamental problem that every single database has to solve. A bank transfer seems simple enough. Step 1, the system withdraws money from account X. Step 2, it deposits that same money into account Y. Easy. But what happens if the system fails right here, after the withdrawal, but before the deposit? This partial execution creates a kind of digital black hole, leaving the database in a totally corrupt, inconsistent state. So how on earth do we fix it?
Well, the solution is built on a single, really powerful promise, an unbreakable vow that the database makes to protect your data. And it's called a transaction.
A transaction basically wraps those two separate steps, the withdrawal and the deposit, into one single indivisible package. And the rule is super simple. Either everything inside this package succeeds, or none of it does. There is no in-between. So if that failure happens, the entire transaction gets aborted, and that initial withdrawal is rolled back like it never even happened. And just like that, your money is safe.
Okay, but for a transaction to be really trustworthy, it has to follow a super strict set of 4 rules. In the world of databases, this is known as the ACID test, and it is the absolute gold standard for data reliability.
ACID is an acronym. It stands for Atomicity, Consistency, Isolation, and Durability. Just think of these as the 4 pillars that hold up the entire structure of data integrity. Let's break down what each one actually does.
First up, we've got Atomicity. And this is that all-or-nothing promise we were just talking about. An atomic transaction is like an atom. It's indivisible. It makes sure that our bank transfer either fully completes with money successfully moving from one account to the other, or it fails completely, leaving the original balances totally untouched.
Next up is consistency. This one is all about making sure the database follows its own rules. So for a bank, the biggest rule is that money is never created or destroyed out of thin air. For example, if account X has $600 and account Y has $300, the total is $900. After a $100 transfer, account X has $500, account Y has $400, but the total is still $900. Consistency guarantees that the database just moves from one valid state to another. The books always have to balance.
Then we have isolation. The best way to think about this one is like a protective bubble. I mean, if thousands of transfers are happening at the same time, isolation makes sure they don't see each other's messy, halfway done work. Each transaction gets to operate as if it's the only thing happening in the entire universe, which prevents them from tripping over each other and corrupting the data. And finally, durability. This is the ultimate promise. Once the database tells you your transaction is committed, which just means it's complete, that data is permanent. It's written down to something that doesn't forget, like a hard disk. And it will survive a power outage, a system crash, you name it. It is safe, period.
So, we've got it. The ACID properties make a single transaction safe. But here's the thing. Modern systems aren't dealing with just one transaction. They're dealing with thousands, maybe millions, all at the same time. And this introduces a whole new level of complexity, the concurrency challenge.
I mean, this is where you get into some classic problems. If 2 people try to book the very last seat on a flight at the exact same millisecond, who gets it? Or if 2 different ATM deposits try to update the same bank balance, how does the database prevent just utter chaos?
If you don't manage this stuff properly, you can get 2 major nightmares. The first is called a lost update. So imagine transaction X reads a balance, but before it can save its change, transaction Y reads that same original balance. X writes its update, but then Y writes its update, completely overwriting and just erasing all of X's hard work. The second problem is a dirty read. This is where transaction X updates a value but then fails and has to roll back. But in that tiny window, transaction Y has already read that temporary dirty value, and now it's running around making decisions based on dangerously incorrect data.
So to prevent these kinds of disasters,
Databases need a sort of traffic controller. And that is the job of concurrency control. It's a set of protocols designed specifically to manage access to data and make sure those rules of isolation are never, ever broken.
The most common tool for this job is locking. And there are two basic types. A shared lock is kind of like multiple people reading the same book in a library at once. It's totally fine because nobody is changing it. But an exclusive lock is like checking that book out to write notes in the margins. As long as you have it, nobody else can even read it, let alone write in it. And this is what prevents those lost updates and dirty reads.
But okay, how are these locks actually managed? Well, a really clever protocol called two-phase locking provides the discipline. In the first phase, the growing phase, a transaction only acquires locks. It gathers up everything it needs. Then, once it releases its very first lock, it enters the shrinking phase, where it can only release them. This simple rule, grow, then shrink, is incredibly effective at preventing chaos.
Of course, there's a catch. Locks have this ironic little side effect called a deadlock. This is where transaction 1 has a lock on data A and is waiting for data B, but at the same time, transaction 2 has a lock on data B and is waiting for data A. They're stuck, waiting for each other forever. Thankfully, databases have some pretty sophisticated deadlock detection systems that can spot these cycles, break them up, and keep things moving.
All right, so we've talked about logical errors and we've talked about concurrency chaos, but what about the ultimate test? What happens when somebody pulls the power cord, the server just dies, and the whole system comes crashing down? This is where the database's ultimate safety net comes into play.
You know, this is just a fundamental truth in computer science. Hardware fails, software has bugs, power grids go down. A reliable database can't just hope for the best. It has to be built with the absolute certainty that it will one day fail, and it has to know exactly how to recover when it does.
And the core of this safety net is a brilliant idea called log-based recovery. It's simple. Before the database ever actually changes your data, it first writes down what it's about to do in a special file called a log. This log is just like an airplane's black box recorder. It's a permanent, step-by-step record of every single change, and it's stored somewhere safe.
Now you can imagine that log could get enormous over time. So to speed up recovery, the system periodically takes what's called a checkpoint. A checkpoint is basically an emergency save point. It forces all the committed changes out of memory and onto the disk, and it makes a mark in the log. That way, after a crash, the system knows it doesn't have to replay the entire history of the universe, it just has to go back to that last known good state.
So, the system reboots after a crash. What happens next? Well, the recovery process is this really methodical three-step dance. First, it scans the log backward from the moment of failure to the last checkpoint. Second, it makes two lists. Transactions that had already committed go on a redo list, and transactions that were still running go on an undo list. And finally, it goes through and undoes all the incomplete stuff, erasing their changes, and redoes all the completed stuff to make sure their changes are definitely saved. The result? A perfectly consistent database brought right back from the brain.
So, from transactions and ACID properties to locking and crash recovery, you can see that traditional databases go to absolutely incredible lengths to guarantee consistency. It's a real marvel of engineering. But all of these guarantees, they come with a cost, an overhead. And that leaves us with a final question to think about. What if a system didn't need that level of certainty? What if for some apps it was better to be incredibly fast and always available, even if it meant the data was only eventually consistent? Now that trade-off, well, that's the story for another time.